Boa tarde. My name's John Hawthorn. I'm a Rails core member, a Ruby committer, and a staff engineer at GitHub on the Ruby architecture team. GitHub is one of the largest and most complex Ruby and Rails applications out there, and my job is to make github.com fast. Basically, I'm trying to avoid you seeing our equivalent of Twitter's fail whale. And performance problems can hide anywhere, and a profiler is the best tool to solve that. Wherever the trouble's hiding, in a library, in a database query, in a network request, a profiler will shows you where your program's executing and what's taking up the time. For the past year or so, I've been working on Vernier, a new profiler for Ruby 3.2 and greater. It aims to deliver more information more accurately than previous Ruby profilers. And it has a fancy new front end that should make it easier to use that we've borrowed from the Firefox team. So let's start with a quick demo, just to see what using a profiler is like. Vernier comes with a CLI to easily measure a command. We're going to measure bundle lock. Bundle lock's pretty much the same thing as bundle update. It updates the versions of your packages, but it doesn't install them. That's just going to be a little easier for us to measure. So we can run that, and after it's finished, Vernier will tell us that it's recorded a result, that the program took about 2.2 seconds, and where it wrote that profile file. So now we need to view this file. And we can take that and upload it to our viewer program, which is a single-page app that is hosted at Vernier.prof, or you can use the profile viewer gem that Aaron's written. This is just a lightly modified version of the Firefox profiler, which you can also use. The file's compatible with theirs. The big difference is we've replaced the word JavaScript with Ruby. If you want to follow along later, this is the bundler demo that's on the Vernier.prof website. So when we drag our file in, this is the first thing you will see. There's a timeline up at the top that shows what the program did throughout its execution. We see the 2 seconds up there. And you can move your mouse over and it'll show a stack trace of what was running at each point in time. The lower part of the screen shows the same information, but with a slightly different visualization. This is the stack chart view, so it layers all the functions that are currently on the stack and their names. And we can zoom in on the upper timeline and scroll through this, and you can imagine your program executing as it goes through the 2 seconds it took to update our gems and get us this result. Now, I find this incredibly powerful. You can really see your program doing whatever it is, and any bottlenecks you have, you can see, as well as just learn about your program in this view. But it's a little busy and intimidating and complex to have on a slide. So for most of this talk, I'm going to switch back to this other view, the call tree view. So the call tree is more like a summary. It shows a top style list of which methods took the most time. And initially it's telling us that main took 100% of our time, which is pretty obvious and like not that helpful. But it's true though. It's just that this is showing us a bottom-up view of our program. And we're indeed starting in main, but to get some more useful results, we can look from the opposite direction. We can look at a more top-down view by clicking invert stack chart. And now this is showing some interesting methods. The first one that comes up is thread queue pop, which means we're probably waiting on some other thread for some data, so let's ignore that for now. The next is weird though, string split. String split is a C function, so we wouldn't expect it to be slow. It's written in C. I don't know of anything that's slow about it, but it's still taking 10% of our time for this command. And the fact that we're seeing it here means that we're probably either calling it with an enormously large string, or much more likely we're calling it way too many times. So we can expand this tree, and it will show us the places which are calling the string split command. And we see two different things show up here pretty significantly. Inside the bundler compact index client cache class. I don't know what that is, but we don't really need to. We can double click on anything in here, and Vernier, the viewer, will bring up the source code. So here we're seeing the source code that took about 10% of the time of our program. On the left in the margins are annotated the number of samples we saw. I'll explain that in a minute, but you can think of samples as a relative measure of how much time was spent running a line. And this doesn't show us the number of times the line ran. Unfortunately, this is not the type of profiler that can tell you that, but instead what it just tells you is about how much time we spent here. And that's split into total and self. Total sums up this line and the things it called into. So this line.split, we see the 315 in the total is the number of samples here. So taking a closer look at this, I think this is great Ruby code. This is the code I would like to write most of the time. The problem is, I checked out how many times bundler runs this in that command, and it's run 200,000 times. And that's a lot of times. So I understand now why this is showing up, even though string split is probably fast. And so our options to improve this is to call this less often, which we might be able to do, but I don't really know bundler well enough. Our other option is there might be a more efficient way to do what this is doing. Here we're splitting a line by spaces into 3 strings, which get returned as an array, and then we just grab the first and last string in that array. We throw away the second, and we don't really need the array other than as a container to return those strings inside. So we can do that a little more efficiently by using a substring to get those strings instead. And this isn't as pretty, and again, this is why it's very nice to use a profiler. You can write the beautiful Ruby code 99% of the time, and then figure out the cases that you actually care about performance. And so let's see how this does. If we time bundle lock before our changes, it takes 2.1 seconds. And if we time it after, 1.9 seconds, so 10% faster. This is why I love working on performance work. We made this 10% pretty significant for a tool everyone uses like Bundler, and people have checked the performance on this. But without even starting with a deep knowledge of how it works, we were able to make a substantial improvement. We've also gained knowledge of Bundler. I want to point out something I didn't do here. I didn't use the profiler to measure the improvement. Profilers all have some amount of overhead and accuracy problems, and we don't want it to look better to the profiler. We want this to actually be faster. And Vernier attempts to be much lower overhead and more accurate than previous profilers. So next I want to look through the evolution of Ruby profilers to see why accuracy can be a problem. So the most intuitive kind of profiler you can make is a tracing profiler. You can have a callback when the method is entered using the tracepoint API, and another callback when it returns. And then you can measure the difference in time and figure out how long it took. This is the Ruby shipped until I think the last version with a profiler like this called Tropical.rb. And you can run it, it's very convenient, but it makes your program 500 times slower. Or at least this program. But you know, maybe that's obvious if you're measuring Ruby and every time you're running a line of Ruby, you need to run an extra line of Ruby. It's going to be much slower. So there's also a C version of the same thing, RubyProf. But even that's 30 times slower. And there's 2 really big problems with having this much overhead in my mind. The first is I can't run this in production. The pages I want to test already come close to hitting a timeout, and at 30 times slower, they definitely will. And production's really the best place to run a profiler if you want to make your code faster in production. That's the only place that's going to show you the correct latencies and problems you're seeing there. The other problem is that on this program, it's 28 times slower, but programs aren't consistent in how much they're made slower. I gave this recursive Fibonacci, which is pretty much the worst case for this type of profiler. But a real Ruby program is a mix of components. Some of its time is spent executing Ruby. Other time is spent running native code, like string.split, which we were just looking at. And generally, the vast majority of the time is spent idle, waiting on a database query to return, a network request, doing file I/O. But a profiler that adds overhead to Ruby is only going to add overhead to the Ruby section. So you might see this as the result of your profile, which just isn't accurate to how your program's working in the real world. If the slowest thing in your request is a database query, I would like to know about that database query rather than some Ruby code. So because of that, to avoid overhead, most Ruby profilers use a technique called sampling, where basically they'll wake up every so often. Here I've chosen 1 millisecond. You could call this the sampling interval or the sampling rate. And on every loop, it will record a sample. So it will get the backtrace from the main thread here and throw it into an array. You could think of the backtrace as if an exception had been raised, or you'd used puts caller, anything like that. So at the end of running this program, we'll end up with a big array filled with samples, which are records of what was being run at that exact point in time. And conceptually, this is how all modern Ruby sampling profilers work. RB-Spy, StackProf, Vernier, they all use this technique. So this is a good mental model to keep in mind when you're looking through a profile. It's being based on this data. So this doesn't include things like how many times a method was called, or if a method was very short, we might not even see it in here. So that's why sometimes profiles can be a little confusing or like they're missing data. Just remember that this is how it's being measured. It's a statistical model. So let's visualize how this works. So we have our running program. Here I'm imagining it doing a sleep 1. And then we run this pure Ruby profiler alongside it, and it will just sleep and record a sample. And for sleep 1, this will record 1,000 samples because we're measuring every 1 millisecond. And this works for sleep 1, but if we try this pure Ruby profiler on a slightly more complex example, like a loop that takes 1 second, but instead of sleeping, it just keeps itself busy, this profiler will stop working. Ruby has a GVL, a global VM lock, which only allows one thread to execute at a time. I think that often sounds to people much worse than it is, and I think this is something people are more, or sometimes people are more worried about this than needs be. Ruby does great with threading. We should be using many more threads than we are, but this seems like a scary problem, and it's certainly something that a profiler should be able to detect, and like this isn't a real profiler, I made it up for this talk. So Vernier is the first profiler to bring GVL information into the profiles it takes. I guess I've made this a little confusing. The Vernier profiler is measuring our pure Ruby profiler, which is measuring a script. So, but it will show us the time it stalled, which tells us why it would not be working. We show threads being in one of 3 states in Vernier. They're either running, which is executing Ruby code. They're stalled, which we just saw. It's blocked on the GVL. This is the only state that's kind of bad. If you're seeing this too much, you're probably, you either have a bad C extension or you're just trying to do more work than you can in your threads, and maybe either your thread count should be lowered or you need more processes. Lastly is suspended, which is when you're sleeping or doing I/O, network, database queries, that kind of thing, or even running some types of C extensions. And this was actually, we had an accidental, I think this might be the accidental best feature of Vernier. Logging all of these times the thread ends up suspended actually ends up showing us every time our thread does any I/O. So Here we're seeing that bundler suspended the thread inside TCP socket initialize. So it's actually showing us, oh hey, bundler was making an HTTP request here. And this is actually the file that it downloaded that had 200,000 lines we were splitting all the strings of. And so this is a really useful, like, we don't have to add extra instrumentation to get this information from all the I/O that happens within your program. So it's the nifty little accidental feature. Okay, let's look at a more realistic profiler. StackProf is the profiler I've used for sure the most of any. It was the direct inspiration for Vernier and was a state of the art for many years. StackProf does its timing using Unix signals. And Unix signals are pretty weird and quirky. When a Unix signal comes in, it immediately starts executing the C code that's registered as its signal handler. So like right in the middle of any other code. And because of that, it's unsafe to do pretty much anything. You're not allowed to allocate memory or do much at all. So we're forced to just use a Ruby API that says, hey, we'd really like to run some code at a point that you determine that it's safe. So we can do that, and then Ruby will eventually hit a point where the VM's in a consistent state, and we can run our code to record the profile or record the sample and save the sample. And this was the best Ruby had for many, many years, and it works quite well. It has no problems with the GVL, but it has a weird bias. Here's a demo program I've made where we're doing a bunch of string concatenation, and then which is slow, and then calling an empty method, which should take no time at all. But the Ruby VM only inserts safe points here, in this particular example, at the end of the two methods. And so the return from the empty method happens before the return from the slow method. So if you profiled this with an older version of StackProf, it would tell you that 100% of time was spent in the empty method, which is just wrong. Slow method took all the time here. And this isn't a problem unique to StackProf. I learned researching this talk that Java has a lot of profilers that have the same safe point bias. So we worked around this in StackProf by moving the frame recording into the Unix signal handler. It was more we buffered up a sample so we didn't have to do any allocation, and then we'd save the sample at a later point during one of these save points. And that removed the bias, which is great, but it was still not perfect. If we had a running program that took a long time to reach a safe point, and this is more often than not was C extensions or libraries like that, it was possible that you'd end up missing samples as another one would come in and it would overwrite the previous sample we'd buffered, and we just miss data. Vernier finally solves this problem. We're reintroducing the second thread, but this time, instead of being a Ruby thread, it's a C thread that's not using any Ruby APIs. This thread's only responsibility is to save the samples that are recorded from the other thread. So this is more accurate. As long as your machine you're running this on is fast enough, we never lose any samples. And there's no bias to them because we never use the SavePoint API. In addition to that, Vernier has less overhead because we don't need to do the work to save the sample inside the main thread. We're only buffering the frame in the main thread, and then an extra thread has to do the allocation and work to save the sample. Speaking of threads, threads are a thing that Ruby profilers have not always been great at. Earlier versions of StackProf only ever recorded the main thread, which maybe 10 years ago in Ruby was fine, but nowadays that Puma's pretty much the default web server, it would give you samples or profiles that had just nothing happening in the whole thing. And so we worked around this a bit by forwarding the signal to the thread that you'd started the profile on, and I think that helped out a lot, but it still left a really incomplete visualization of what your program was doing. Because if you were running a multi-threaded job server, or if you spawned threads to try to do things in Puma, it would just not show you. Or even if Puma was serving 2 requests at a time and you had some GVL contention, that would be invisible to you. And so one of our principal goals with Vernier was to measure every single thread in the application at every point in time. And we were able to do this, but one worry we had early on was that this would introduce a lot of extra overhead because we'd need to sample each of the threads and do however many threads you had running times the amount of work you would otherwise. But we eventually realized that there's a trick you can do, that idle threads which have released the GVL, aren't allowed to execute Ruby, so we don't need to measure them. This doesn't mean we don't have the information from them. We know exactly what that thread's doing. It's doing the same thing it did when it released the GVL. And so let's see the end result of all of this. Here's what you can do with Vernier that no other Ruby profiler can do. We can select the extra threads which are running by going to this track selector in the top left. And we see, in addition to the main thread, 3 other threads here. 2 that are started by bundler and 1 from the timeout library, which we probably don't care about. So we can select those 2 extra threads and see them show up in the timeline view. We can then zoom in the timeline view to look at that section where those 2 threads were running. They only started in the middle of our program. It didn't last too long. So here we still have the main thread selected, and we're seeing now in the call tree that 60% of time was spent in thread queue pop. So that thing we saw earlier that was our top thing blamed. And since thread queue pop is here, let's look at another thread because we're probably waiting on data from it. I'll just grab the first one. And here we're seeing string.split again. And if we expand that, I think it's a different cause this time. Yeah, it's a different thing that's being parsed. But I promise the point of this talk isn't don't use string split. String split is great. The reason bundler happens to have this is bundler can't use JSON parsing or things like that because it's installing the JSON parser. So it's just doing ad hoc parsing. And if you want to improve bundler, I haven't looked at these ones yet, so I'm sure there's an opportunity there. A couple more features Vernier has I'm just going to skim over. We have GC instrumentation. So just like the GVL, the garbage collector is something that I think people fear from the Ruby VM. But with Vernier, you can just see when it's paused and determine whether it's really something you need to worry about in your request. And if the garbage collector is taking a great deal of time, we can do allocation tracing. Vernier supports doing allocation tracing at the same time as timing. We don't have it on by default because it adds a little bit of overhead, but you can record in the same file both the time things took and the number of objects each method took. So if you're seeing too much garbage collection, you can solve it with this. We also are able to hook into Rails. The Rails active support notifications framework is a tool that measures various things that happen in Rails, and other libraries can publish to it too. It's the thing that prints out the queries if you are using development mode. So we listen to this even in production, and so when you see a database query taking up time in your timeline, you can go over to this view and see actually which SQL it was and optimize it there. This is this is what I want Vernier to provide, to be able to measure with a single file a whole request or a minute of your web server or some amount of time on something you want to make faster and get a really complete visualization of everything that was happening and know everything you need to make your code faster. I hope you'll give profiling a try, and especially using Vernier. Not only can it help you make your program faster, but understand it better. Usually the most important parts of a program are the ones that are taking time. So I hope you'll try this out. Let's write fast Ruby. Obrigado.